All right, section 1.8, video 2. We've talked about continuity and the definition of continuity now on open and closed intervals. You kind of need to use the combination of those to do this next example. I am not going to walk through the entire example all the way through. It's really just not worth it. But what we've got is this function, which is 1 minus square root of 1 minus x squared. Don't expect that you guys are going to know what that looks like, so I'll sketch it for you. It kind of looks like a parabola, even though it's not. But we're only going to go from -1 to 1. And if you plug in -1, you're actually going to get out 1. So we'll say that that's 1 right there. Then if you plug in +1, you'll also get out 1. If you plug in 0, you're going to end up with 0. This is why I said it kind of looks like a parabola, even though it's not. It just kind of looks something like this in between. So notice that what we have is a closed interval. In order for you to actually be able to show the continuity of this function, you would have to show, first of all, that it's continuous everywhere on the open interval from -1 to 1. Basically, you would have to show that everything in between the two endpoint dots is continuous. Well, we can obviously clearly see it from our graph, but there's nothing that's going to make it undefined in between -1 and 1, so it would be continuous. Again, I'm not showing the actual mathematical proof. I'm just kind of going through what you would do. Then you would actually have to show the continuity at the endpoints. So we're going to say that it's continuous on the open interval. We'll say continuous here. But now you have to show the continuity at the endpoints. To show continuity at 1, you have to show that the limit here as x approaches 1 from the left side, only way you can do it, so you do the limit as x approaches 1 from the left of our function, well, that has to equal the function's value there at 1. And it actually does equal f of 1, so that would be good. So it's continuous at the right endpoint. Likewise, you would have to show the limit as x approaches -1 from the right side, because the only way you can approach -1 is from the right side of it, of f of x. Well, that has to equal the function's value at -1, and they do, because in this case, both of those are 1. So that would be how you would actually show the that this is continuous on the entire closed interval. Again, I'm not going into all the specific math about that, but hopefully that gives you a general idea of what you would have to do. All right, so there's a theorem here. Properties of continuity. Some notation that you've probably never seen before. If B is an element of, that's what this means, is an element of, that capital fancy looking R means all real numbers. So if B is an element of all real numbers, basically it's a really shorthand notation of saying B is a real number. If B is a real number and F and G are continuous at A, then the following functions are continuous at A. And we're going to use C as a constant in this case. So scalar multiple, basically that means any kind of a multiple C times f of x is going to be continuous. If I were to take any continuous function and add or subtract it to another continuous function, the resulting function will still be continuous. Product is the same way. If I take a continuous function and I multiply it by another continuous function, that will also be continuous. The only one that has any kind of an issue is the quotient, which says that if I take a continuous function and I divide it by a continuous function, that will also be continuous unless g of x equals 0. So g of x here cannot be 0, because technically g of x equals 0, or in other words, thinking of y equals 0, that's a continuous function. It's just the x-axis. So that's the only thing that would limit that one. Okay, really easy theorem, nothing you really have to memorize, just kind of know that that makes sense. At least I hope that it makes sense. So the following functions are continuous at every point in their domain. Polynomials. Polynomials, by definition, have only whole number exponents. So 0, 1, 2, 3, 4, those can be exponents of your variables, nothing else. So all polynomials are continuous everywhere. Rational functions. Rationals are polynomials divided by polynomials. So in the domain, as long as the polynomial itself does not create 0, then the rational function will be continuous everywhere. So in its domain, a rational function is continuous everywhere. Remember that a rational function can have a 0 in the denominator, so if that's the case, it would not be continuous there, but then that would be out of the domain. A radical function, which is something with a root in it. So all radical functions, again, are continuous everywhere in their domain. As we know, radical functions have limited domains for even-powered radicals. So anywhere in the domain, they're continuous. And then trig functions, anything in its domain is continuous. We do know that there are asymptotes, but other than the asymptotes, they are continuous. All right, so our next theorem, continuity of a composite function. So a composite function is a function evaluated at another function. So we're going to say if G is continuous and C and F is, if G is continuous at C and F is continuous at G of C, then the composite function, which is given by f of G of X, or probably better written like that so you can see which function is plugged into what, that is also continuous at x equals c, or at c. So one benefit of the last theorem is that if f and g satisfy the given conditions, you can determine that the limit as x approaches c of f of g of x is just directly substituting in c. It's f of g of c, and that's because g is continuous at c, f is continuous at g of c, therefore the whole thing is continuous. You just plug c in. So how would something like that work? Well, if you look at number 1, f of x is, g of x, we'll go with the inner one. G of x is a linear function. It's continuous everywhere. F of x is a quadratic. It's also continuous everywhere. So compositing those two things is going to be continuous everywhere. So h of x, which is f of g, so f of g is going to be x minus 1 squared, substituting the g function into the f function. That is continuous everywhere. Continuous everywhere, or everywhere continuous. You pick. All right. Number 2, however, has a little bit more of an issue. G of x is quadratic. It's continuous everywhere. F of x, however, has a discontinuity in it. If you're looking at it, remember, G is getting plugged into F. So let's go ahead and write h of x out here first, just so we know what we're looking at. H of x is f of g. So it's 1 over, and then we're going to plug in x squared plus 5, where the x is, and then subtract 6. So that's what h of x looks like. Again, g of x is continuous everywhere. So g is going to be continuous at any value that we want because it's quadratic. F of x, however, is not. It's got a discontinuity at x equals 6. So in this case, x cannot equal 6. However, when we formed h of x by doing the composition, we actually come up with, if you simplify that, 1 over x squared minus 1. And we know that that is also discontinuous when x equals 1 and negative 1. So we also have to say that x cannot be plus or minus 1. So you have to check both of the originals. Specifically, you have to check which one is the interior one, which one is the exterior one. You have to eliminate whatever discontinuities you might have from the interior and the exterior, but then you also have to eliminate the discontinuities that might be formed after you do the composite. All right, so that one's a little bit different because it's not continuous everywhere. It's continuous everywhere except those values. Right, you probably really won't come across that too much, but it is possible. This next theorem, this is really important. This is probably one of the more important theorems that we do. So this one, you are going to want to put a big old star by. We need to know this. It's called the intermediate value theorem. And again, there's going to be an awful lot of mathy speak here for something which is really not that difficult to understand. So I will try and put it in everyday terms after we go through the math stuff. So it says, if f is continuous on a closed interval a to b, we kind of know what that is by now, and k, again, who knows why, k is some number in between f of a and f of b. Well, wait a minute, now it says k is a number in between f of a and f of b. Well, f of a and f of b are y values, so that actually makes k a y value here, where f of a does not equal f of b. So whatever those two y values are, they cannot be the same. So k has to lie in between two y values, and the two y values cannot be the same. Then there's at least one number c on the interval from a to b. So if c is in between a to b, that makes it an x value, such that f of c equals k. All right, what the heck does all that stuff mean? All right, let's try and figure it out. So if we've got, I'm just going to try to make this relatively easy for the first one here. I'm going to make a linear function, something that looks like this. And we'll say that this is A. We'll say that this is B. So there's our closed interval from A to B. We'll close it off by putting two little dots there, even though the whole function is continuous, but that doesn't matter. We'll close it off by A to B right there. Well, if I were to draw something from here and then come over here, that's going to be f of b. That's the y value associated with plugging in b. Same thing here with a. Draw the line over here, that's f of a. Okay, according to our theorem, f of a and f of b cannot equal each other. We're good there. I've got to have some number k which is in between f of a and f of b. What it's saying is there's at least one number c in between a and b. So we're going to put a c someplace in here. It doesn't matter where. I'll just put c there. In between a and b, such that now if I were to draw this up here and hit the curve and find the y value associated with that, that value has to be in between a and b. We call that one k. And it is. If you were to draw that c anywhere in between a and b on the x-axis and put it up to the function and move it over to find the y value, that k value would be in between f of a and f of b. In other words, no matter what you have, if you have a closed, continuous function, every y value has to be taken on in between f of a and f of b. So the lowest y value and the highest y value, every possible y value has to be in there somewhere, and they're calling that value k. Let's look at one more quick example of that. So let's draw something which looks a little bit different, maybe something like that. So now I'm going to put, so we use blue on that one, so let's just still stick with blue. So we'll say that, this is A. We'll say that, actually, no, I don't want to put A there. I apologize. Let's put A way over here to the left. Let's actually make it somewhere in the negatives. And we'll put B like someplace way out here to the right. So if I were to go up here and put a dot where A is, looks like A might be there. Looks like B might be way up here. So now it's closed between A and B. Well, let's find f of A and f of B. Let's draw our little dotted lines. F of A is right here. That's the y value associated with A. F of B is probably going to be above. No, it's going to be pretty close. There's f of B. So f of B and f of A are different values. They're definitely different. So according to this, if I put C someplace in between A and B, I'm going to go ahead and put C right here. According to this, if I go up to the graph, my K value, my Y value, my K value here has to be in between f of A and f of B, and it is. But the interesting thing about this is there's more than one C that this holds true for. C could also have been here, because as you can see, that exact same Y value is in different places. Well, C could also exist over here. So I have a whole bunch of different places that I could put C. It's not telling us that there just has to be one C, but there has to be at least one C that you're going to get a K value in between f of A and f of B. I know, could be a relatively confusing topic. This is something you're definitely going to want to look further into if you need to go back and rewatch it a little bit till it sinks in. But ultimately what it's saying is every Y value between the lowest Y value and the highest Y value on a continuous closed interval has to be taken into consideration somewhere. It will exist. All right, so let's actually work out a problem. Oh, sorry, I skipped the bottom of that page. So the intermediate value theorem guarantees the existence of at least one number C on the closed interval from A to B. There may be, as we just saw, more than one number C such that f of C equals K. All right, now let's move on. So let's actually do one of these. It's actually really simple to do something like this. Verify the intermediate value theorem applies on the indicated interval and find the value of C guaranteed by the intermediate value theorem. So for the intermediate value theorem to apply, if we go back to the rules, it says it has to be continuous on a closed interval. Well, they gave us a closed interval from 0 to 5. And I know that it's continuous because the function itself is a quadratic, which is a polynomial. Continuous everywhere. Again, that's one of our theorems. Okay, the other thing it says is that f of A and f of B cannot equal each other. Well, it means we have to find f of A and f of B. So f of A is f evaluated at the left endpoint. That's A. So f of 0, plugging 0 into f of x is going to give you -1. Okay, you should probably be able to do that without thinking too much. F of B, which is your right endpoint, is f of 5. Okay, you have to do a little bit of thinking here. If I plug 5 in, we're going to get 5 squared, which is 25, plus 5 more is 30, minus 1 is 29. So very clearly, f of A and f of B do not equal each other. Okay, we're good there. So that's all the criteria. Now, according to the intermediate value theorem, it says that if we want to verify that f of C equals 11 somewhere, well, that means I need to actually figure out where this function equals 11. So is 11, first of all, a number in between my two endpoint values? Yes, between -1 and -29, excuse me, -1 and +29, 11 definitely is in there. So we're good there. So we need to take the function x squared plus x minus 1 and set it equal to 11 so that we can figure out where these values actually occur. Okay, so now we just have to solve the quadratic. Since it's quadratic, we'll subtract 11 from both sides, get one side equal to 0. This is probably the easiest way to solve this one. This one actually factors nicely. That'll be, what, x plus 4, x minus 3. So I know that x is going to equal -4, or x is going to equal +3. And since we're looking for the ones that are guaranteed by the intermediate value theorem, they have to be on our original domain. Our original domain was from 0 to 5. Well, x equals -4 does give you a value here of 11, but it's not on our domain, so we're going to get rid of this one. It's not really included. So our answer is that C equals 3. It's the C value. -4 is out of the domain. So C equals 3 is our value that is guaranteed to give us that value of 11 by the intermediate value theorem. Okay? Let's go ahead and do another one. f of x equals x squared minus 6x plus 8 from 0 to 3. So once again, this is pretty clear that it is continuous because it's a polynomial on a closed interval, 0 to 3. And we're going to double check the endpoints. So we'll do f of 0 and f of 3 and make sure those two things are not the same. So if I plug 0 in, I get 8. If we plug 3 in, that's going to be 3 squared is 9 minus 18, which is going to be negative 9, plus 8 is negative 1. So f of 0 and f of 3 are clearly not the same. So we can use the intermediate value theorem. It will apply as long as this is in between these two, and it is. So we're good there. So we're going to take x squared minus 6x plus 8, set it equal to 0, and find the values that work. Again, this one happens to factor pretty nicely. X minus 4, x minus 2. So x is either going to be 4 or x is going to be 2. Double check to make sure that those things are in your domain. The original domain here was 0 to 3, so I don't have to worry about the 4. So C is going to be 2 only. Again, not really difficult to do the intermediate value theorem. And this one really has a lot of uses when it comes to determining whether something crosses the x-axis or not. And I think we'll probably get to something like that eventually. So note that the intermediate value theorem tells you that at least one C exists, but it doesn't really give you a method for finding C. In this case, we were able to use factoring, but there might not be a very easy method if things don't factor nicely. So such theorems are what are called existence theorems. Meaning that sometimes it's only going to tell you that there is a way to, that there's an existence of a C value. Maybe it doesn't tell you how to find it. All right, this video is already over 22 minutes, so I'm actually going to stop it here and come back with a third one, which we should definitely be able to get done in much less than 10 minutes.